What kind of reaction is this?
Yeah, I put answers on there. Oh, yeah.
It's called a neutralization reaction. Okay. And let's dim the lights a little bit for mood, for better. Okay. What's going to happen? This is a subset of the double replacement. This is a strong acid. How do I know it's a strong acid? It's on the table. This is strong base, and then I formed a solid plus water. Okay, I'm going to do a titration with this, which you've heard that term before, but I'm going to do it in a funny way. Not with an indicator, but with a light bulb. This is a strong or weak electrolyte? Strong, so it separates out into ions. I know that from page 32. So I get a light bulb shining because it conducts electricity. You got that? I'm going to add H2SO4. What's going to happen is I'm going to do this reaction. Are these strong electrolytes? Neither of them are. Is that okay? Neither of those products are strong electrolytes. So when I get to the point, I'm going to slowly, right now, start adding my strong acid. When I get to the point, I'll turn this a little bit so maybe it's easier to see the light bulb. So I'm slowly, right now, adding the strong acid. And what's going to happen is as we get to the products, because the products are weak electrolytes, you'll see the light bulb get more and more dim over time. Until I've completed the reaction, the light bulb will nearly go off. Do you see that happening? So the light bulb's nearly off right now because the reaction is pretty complete. And I'm going to keep adding more, so when there's only products, it'll turn off. But at the very end, if I keep adding too much sulfuric acid, if I add too much sulfuric acid, is sulfuric acid a strong or weak electrolyte? Strong, so it's going to get brighter. And you see it getting brighter right now. That means the reaction has finished, and I've added so much sulfuric acid, it's in excess, and the sulfuric acid is now causing it to conduct electricity. Does that kind of make sense? So I'll just re-say it. You saw the light bulb go on and off. I'll restate it again. I started with only barium hydroxide in the bottom. It was bright because that's a strong electrolyte. I know on the video you all can't see this. And then I added sulfuric acid because the reaction was occurring, producing weak electrolytes. The light bulb went almost off. And then because I added too much sulfuric acid in the end, the light went back on because I had a strong electrolyte again. Okay, so that's that. That was kind of a funny titration where we did it with a light bulb actually. All right, let's turn that off. Cool, let's keep on going. I'll just toss a couple of these up here if you want to see some examples. I already talked about that last one. There's a lot of common, really great uses for acids and bases industrially as fertilizers, laxatives, batteries, car acid batteries, other acid batteries, lots of things. In soda, there's acid. That's what gives it that tart taste. I'll just give you one example of a strong acid that is not on that table. It's pretty rare, that's why we don't need to list it. But it's called a superacid, really. And there's super bases too. This is a superacid. It's the strongest superacid known. And it's so strong. You know sulfuric acid, which is a strong acid? In lab, you're only using 6 molar. That's super dilute strong acid in lab. This is 20 quintillion times stronger than 100% sulfuric acid. So that would be 100% sulfuric acid is like a sludge almost. And so we can't even use the pH scale because it goes off the scale on the bottom side. So there's this Hammett acidity function that we use. You might be wondering, how the heck do I even like contain this? There are uses for this right here to protonate hydrocarbons, which is an OChem thing. And there are containers, like a Teflon type container, that will actually be able to contain it and is not harmed by it because it's so neutral. So there are things like that out there. You can just look on Google or Wikipedia if you want to see other examples. Strong acids and strong bases, super acids and super bases that exist out there. Let's just, for fun, let's check this out. You throw up for whatever reason, who knows why. You're probably not going to drink orange juice or lemon juice, or lemonade, I guess, because yeah, your throw up, the stomach acid that's also coming up with the vomit is acidic. So you're adding more acid to the scenario, okay? So you're probably going to drink something to dilute that taste in your mouth that is slightly less, either less acidic like apple juice or water, and that just works by pure dilution, like in chapter 4, where we dilute stuff. So weaker acidity juices like 7-Up, apple juice, things like that, or water will help dilute that. If for some random reason you would go somewhere and then come back home and throw up. Okay? All right. Next section. Section 4 and 5 together. Section 4 and 5 together. This is page 37 of the reader and 167 and following in the textbook. And this is a new type of reaction for us called a redox reaction. Now, a redox reaction, it can be another type of reaction too. Sometimes the redox is also a single replacement, but it can also be its own entity. Okay, so this is another type of reaction we're learning. What is it? It's when the oxidation states change in the reaction for multiple species. So when the oxidation states change, the one species will oxidize, and that means the oxidation state goes up. And hopefully that makes sense. You oxidize when your oxidation state increases. The other species will reduce, meaning its oxidation state numerically reduces. Okay? And it's as simple as that. When the oxidation state goes down, it's a reduction. When it goes up, it's called an oxidation. So what does that cause? That causes an exchange of electrons between two species. So one species is giving electrons up. That's the one that's oxidizing, it's losing a minus charge. And the other species that's reducing is receiving those electrons. Well, when there's a movement of electrons, there's a conducting of electricity. And so these, if you got a battery, this is what's going on in any battery you have. There's an exchange, there's a redox reaction going on, whether it's your AA battery that has solid in there, or your lithium-ion battery, or whatever. There's an exchange of electrons causing that movement, causing a voltage potential, and the reaction occurs. And it gets super interesting in Chem to see, you can actually calculate this. You're going to do this for different batteries. It's pretty interesting. We're just going to do the reaction. I wanted to tell you what it was about, but we're just going to do a reaction. Every reaction we've balanced so far, it has a certain term. It's called balancing by inspection. Meaning you're looking at it, there's 3 carbons here, I need 3 carbons there. That's the inspection method. That method almost never works for this type of reaction. So there's a special method we use called the half reaction method in our class. There's actually other ways to do it, but this is the way the book does it, and to be consistent, and this is the way most people typically balance these. It's, I believe, the easiest way. It's called the redox half reaction method. How does that work? Sweet. Here we go. This is also in your textbook in your reader on page 38 as a flow chart. In your textbook, I think they write this out in words, and they write out in words on page 173. So either page 38 or 173. How do you do this half reaction method? Here's what you do. You split the reaction into half reactions, by following the Sesame Street example of like things go with other likes. Okay? And you'll see how this works. Then, you balance each half reaction separately. You split it in half, and so thus they're called half reactions. There's 4 steps to balance a half reaction. Step 1, whatever is not oxygen or hydrogen, you balance that by inspection, like we did before. Step 2, you balance oxygen. But you can't just balance it by adding oxygens, because in solution, which is what we're going to be working with, you're not just having oxygens fly around, but there is water in solution. So you're going to add liquid water to balance oxygen. Because you added hydrogen in the water, now you have to balance hydrogen, because water has H2 you're adding. So you're going to balance hydrogen, but there's not just lone hydrogens around the solution. So you're going to use H+, and that, remember, is acidic. So you're going to use H+ to balance the hydrogens. And then step 4, you're going to balance the charge, and that's with electrons. Okay? Because there's a lot of electrons going around. So, then what do? You're going to use your simultaneous reactions concept that we just learned. And you're going to use that to take 2 reactions that are simultaneously happening and combine them into the overall reaction. Same way. But in this case, the electron's the intermediate. So, am I going to see an electron in my overall reaction? No. If you do, you've messed up. You will see an electron in your half reactions for sure. And there could be other reactions that you see it in, but not for our overall reaction. And then, once you've done that and simplified, you have what's called the acidic conditions answer. Why is it the acidic conditions answer? Because of step 3, where you added acid. Now, sometimes a reaction might occur in basic conditions. If you need a basic conditions answer, you continue from the acidic conditions answer. So, there's ways to go straight to it, but I think it's easier just to continue. So now, you're going to find the number of H+, and you're going to add an equal amount of hydroxides to both sides. You add it to both sides, that retains the mathematical integrity. And then you're going to use that equation at the very bottom of the screen that's bracketed. I'll move it up a little bit. But H+ and OH- has a huge equilibrium to the right, forming water immediately. Okay? So whenever you have H+ and OH, H+ is going to go away, which is what we want. You're going to simplify a little bit, and then you'll have what's called a basic conditions answer. Okay? Basic conditions answer. So this is the flow chart, also in your reader and all that, that we're going to follow in order to balance what we call a redox reaction. Let's try this. This says CN. My whole punch was in an unfortunate location. Remember, I'm recording lectures, so you can always go to YouTube to re-watch something you feel like you might have missed or you want to hear again. I try to post them the next afternoon, or, the same afternoon. Just takes a while to compile such a long video. And there's a ton of examples I have online, by the way, Redox 1 through 8, and they vary in levels of difficulty. So if you look up Redox, there's a lot of them. Okay, some are more difficult than others. We'll try to do a couple difficult ones in class. This one's a pretty average one right here. Okay, how do you know you might have a redox reaction? You know that you might have it because you see a lot of charges around. Like, what are those charges doing there? That clues you in to think maybe this is redox. Now, how do you double check that? Well, go into your reaction and look at the oxidation state of every compound, every element really. So zinc is 0, it's a lone element. This zinc, I'll do it, it's easy, I can do that, 2+. How about that oxygen right there? Not 0. NO, so what's the O? Yeah, oxygen's usually -2, so nitrogen must be +2. Oxygen's usually -2, so this nitrogen must be +2. plus 5. Okay, make sure you can do that stuff. This is just what we were doing in chapter 3 when we were finding out oxidation states. Okay, now notice this. Zinc just did what? It increased oxidation state, so we call that oxidized. Nitrogen just reduced. So there's going to be exchange of electrons as those oxidation states of nitrogen and zinc changed. Oxygen did not change in this example. Okay, so I can write my oxidation half reaction. I'm now going to follow my flow chart to balance this, which is zinc goes to zinc 2 plus. So I put likes with likes, and that's the zinc. And then I'm going to write my redox, my reduction, half reaction I mean, right here, NO3 minus goes to NO. Okay? So I got both of those half reactions now. Now that that's done, let's balance each separately. Let's do, I think the bottom one first. Let's do the bottom one first. Step 1, balance whatever is not oxygen or hydrogen by inspection. That's nitrogen, and there's 1 nitrogen on each side, so we're good with step 1. Step 2, balance the oxygen. Oxygen, there's 3 here and 1 here. I need to balance that with water, so I need to add 2 waters. Now there's 3 oxygens on each side. Step 3, balance hydrogen. There's 4 hydrogens on the right, so I need to add 4 on the left, but not just H's, they need to be H pluses. Okay, step 4, balance the charge. At this point, the overall charge on the right-hand side is 0. That's the easy one, that's why I'm doing it. On the left-hand side, what's the overall charge right now? Plus 3, because there's 4 H pluses and 1 NO3 minus, so plus 3. So to get the same charge on each side, I must add how many electrons here? 3. Is that okay? 3 electrons. Here's a general rule. Every problem I've ever done, the H plus and the electrons are on the same side. There could be an exception, I have not seen it yet. But I've always seen that these 2 things are on the same side. Just from experience. Okay, let's do the top one now. Step 1, balance whatever is not oxygen or hydrogen. That's zinc. There's 1 on each side. Step 2, balance the oxygens. It's done, there's 0 on both sides. Step 3, balance the hydrogens. Done, there's 0 on each side. So I skipped 1 through 3 because it's already balanced. So only step 4, I need to balance the charge. Electrons go on the right or left. Good, I asked. Electrons are minus, remember? Here's one other thing. The electrons down here and the electrons up here better be on different sides or you messed up. Electrons must be on different sides or you definitely messed up. Okay. Now, let's get a different color pen. We're going to combine these by multiplying the top by 3 and the bottom by 2. That'll give my intermediate E, electrons, the same number and causing it to cancel. I want the electrons to cancel. So if there's 6, which is the lowest common multiple, it'll cancel. Okay? So now that I've got my multipliers, let's add this craziness, these 2 simultaneous reactions here. Okay, so when I add them, let's write all the reactions first. 3 zinc plus 2 nitrates plus 8 H plus. There's all the reactants, now all the products. 3 zinc 2 plus 2 NO plus 4 H2O. Now let's put our state symbols in. Zinc is it's a metal, it's a solid. Nitrate, ion, is an ion. All ions, let me do all the ions now, must be aqueous. So those are easy, all ions are aqueous. Water, you know, is a liquid. And then NO, you know, is the gas from standard conditions. So it was given up at the top, but you didn't even need to know the state. You didn't even need to be given it, because you theoretically should know it. Yes? Why is zinc a solid here? Because it's a metal. Why is it aqueous here? Because it's an ion. It's the charge causes it to be a totally different state. Yeah, it's a question. What did the charge do? That's what changed the state. So you have an ion, it has to be aqueous. Let's try another one. This one we're going to do basic method. Ready? Okay. Let's do this. Iodine is -1 here. -1 here. What is it here? 0. It's elemental form. Manganese, oxygens, I'll do the easy one. It's -2 and -2. Okay, what's manganese right here? +4. 4 minus 2 times 2 is 0. What's manganese here? Plus, not 3. Not 1. 7. Plus 7. 2 times 4 is 8. 7 minus 8 is -1. If you can't do that in your head, it's totally fine. You should write it out. Make sure you know how to do oxidation states. So, manganese does what? Reduce. It goes down. It reduces its oxidation state. Iodine goes up in oxidation state, so we call it oxidation or oxidizing. So the oxidation half reaction is I minus goes to I2. The reduction half reaction is MnO4 minus goes to MnO2. Put likes with likes. Okay, now let's do the first one. Step 1, balance whatever. I hope you get this burned in your brain. Step 1, balance whatever's not oxygen or hydrogen. That's iodine, so I must put a 2 here by inspection. Step 2, balance oxygen. There's no oxygen. Skip it. Step 3, balance hydrogen, but there's no hydrogen. So skip that. Step 4, balance the charge. Is an electron's going to go on the right or left? 2 minus here and 2 minus here. Okay? As long as it's the same on both sides, you're okay. Okay, reduction now. Step 1, balance whatever's not oxygen or hydrogen, that's manganese, and there's 1 on each side. That's good. Step 2, balance the oxygen. There's 4 on the left, there's 2 on the right, so I'm going to add 2 waters to the right-hand side. So now there's a total of 4 oxygens on each side. Step 3, balance the hydrogen with H+. There's 4 hydrogens on the right, so 4 hydrogens on the left, but in the form of H+. Step 4, balance the charge. The overall charge on the right is 0, and on the left is +3, so I must add 3 electrons to get the same charge on each side. In this case, it's 0 on each side. Okay, now let's do our multiplication and adding these simultaneous reactions up. This is 2 here, and my other intermediate is over here as a 3. The least common multiple will be 6, so it's a 3 and a 2. Multiplying, that'll cause my electrons to cancel. So, let's see what I get. 6 iodide ions plus 2 permanganate ions plus 8 H plus ions goes to, now all the products, 3 I2 plus 2 MnO2 or manganese 4 oxide, and then plus 4 water. Is this my answer? No, because they asked for basic conditions, and I have H+, that means it's acidic. So I need to go on. And now continue to follow the flow chart, but now for basic, I look for H+, it's right there. And I add hydroxides to both sides. And I add to both sides to retain mathematical integrity. And there's 8 of these, so I'm going to add 8 hydroxides, because there's 8 H+. What does that do? Well, to get a different color here, these form how many waters? Yeah, please don't say 16. Forms 8 waters. Okay? And then now let's just write it out. This is 6I minus plus 2 permanganates plus now 8 H2O goes to 3I2 plus 2 manganese 4 oxide plus 4 waters plus 8 hydroxide ions. Okay, you can see some stuff will cancel, specifically the waters. The 4 waters here will cancel with 8 here to get 4 on the left. And I think that's the only thing that cancels. Let's go to the next page. We've got 6I minus, that's aqueous because it's an ion, plus 2 permanganate ions, that's an ion so it's also aqueous, plus 4 waters, water's a liquid, and that goes to 3I2, iodine diatomic is a solid, plus 2MnO2, this you probably have to be given, but it's a solid, plus 8 hydroxides, and that's aqueous because it's an ion. And now I have my basic conditions answered. That's a great place to stop. By the way, if you're going to study this weekend, Exam 1 will go from Chapter 1 through Chapter 5 redox. Stop including redox. Okay? We will include redox in 1 week on the exam.